Okay, let's get started. We have a lot of class material today, and we have a bunch of announcements too. So homework 3 is due today, as you can tell from the piles, and if you haven't turned it in, you should turn it in within the next 5 or so minutes. We're going to collect it in about 5 minutes. Your project milestone is due a week from today, so next Tuesday. So remember to get that done, don't put that off. There's going to be a midterm review session tomorrow night. Jeff's going to give one from 5 to 7. The classroom is in the email he sent, so I don't remember off the top of my head, but he sent an email with information.
It's the Malden Auditorium on the first floor of Newell Simon.
The Malden Auditorium?
Yeah, it's when you get off the elevators on the first floor of Newell Simon, you just turn left and it's right there.
Okay, so at first floor of Newell Simon, Malden Auditorium. Jeff is going to be giving a review session tomorrow evening, and next week I will likely give one, but make sure you attend Jeff's, if you can't attend next week, that is. Or even attending both wouldn't hurt, certainly. And the format is just going to be pretty much open question and answer. So if you have lingering questions and you can't make office hours, or you want to see it in a longer format, then come tomorrow. The midterm, what does it cover? We've decided the midterm is going to cover up to the end of duality, so through the end of this week. Okay, so everything from the first lecture through what will be lecture 18. And the last announcement is that we had some lectures up on YouTube. Jeff wanted to increase his fan base on YouTube, so he put them up there. So go give him a thumbs up and help his rating out. I think we're going to be putting most of them up on YouTube from now on. Is that right?
Yeah, I'm going to try and put them all up from now on.
Okay. So that was it. Do we have any questions, administrative questions, before we start, or just any questions?
Yeah. First question is, why did Jeff get the room wrong? It's 1507 Newell Simon, not the Malden one.
Okay. So correction is that the review session will be in 1507 Newell Simon Hall tomorrow from 5 to 7 p.m. That's also in the email he sent, so in case you just want to look that up, double check. Okay, so the next 2 lectures, just to give you an idea of what's going to happen, are going to be a lot faster paced than we had previous lectures, and you're not expected to retain or completely understand every single detail in these next 2 lectures because we're talking about a lot of things. And I'm going to try to do my best job to emphasize what's important and what's not. But you can think of today's lecture, which is about duality correspondences, as what are all the different types of duality that we encounter in optimization, and also somewhat outside of optimization, but that are relevant. And the idea is, well, to try to connect these, but also to try to give you help in deriving duals. So it's all the tricks that you're going to need and that you're going to kind of employ in the future for deriving dual problems. And hopefully this sequence or this lecture today will serve as kind of a neat reference for you to come back to either later in the course when you're having trouble deriving a dual, or maybe later on in your research when you're stuck on something and you want to remember one of the rules or one of the correspondences that we learned. Thursday's lecture is going to be kind of an exhibition of dual uses. So I'm going to go over a lot of examples of how we actually use duals and the dual problem and how it helps us both in theory and in practice in terms of algorithms also. And like I said, there's going to be a lot of material, so I'm going to emphasize what's important and what maybe is less important for the sake of the midterm, say, or even this class. Do we want to collect homeworks now?
Yeah, let's go ahead and do that. So anybody who hasn't handed in homework, this is your last chance before getting a late today.
I got these.
All right.
Okay, so just a brief review of what we did last time. We talked about the KKT conditions last lecture. We looked at a general problem of this form where we minimize a function subject to a bunch of constraints, inequality constraints and equality constraints. And we didn't assume a priori that the problem was convex, namely that these functions f and h were convex and that Lj were affine. And then we talked about the set of conditions called the Karush-Kuhn-Tucker conditions, named after 3 people who studied them. The first is, if we think about all these functions with respect to x, if I take a subgradient of the Lagrangian, then that has to contain 0. That's one condition. It's called stationarity. The second condition is that if I multiply each dual variable ui by hi evaluated at x, then it has to give me 0. That's called complementary slackness. So it has to say that either the dual variable is 0 or the constraint is tight. It can't both be that the constraint is loose and the dual variable is non-zero. The third condition and the fourth conditions are just that x and these dual variables u and v were feasible for their respective problems. So x is feasible for the primal problem, satisfies the constraints, and u is non-negative in every coordinate. So that suite of conditions were called the KKT conditions, and we proved that they were necessary for optimality. So if these are satisfied, then x is primal optimal and uv are dual optimal under strong duality. Remember, strong duality occurs in, for example, if the functions are convex and Lj are affine, and the primal problem, say, is strictly feasible over the inequality constraints, then we get strong duality. It's something called Slater's condition. So under strong duality, these are necessary for optimality, and they're sufficient for convex problems. That's something that we talked about last Thursday. Questions about that? Okay, we didn't talk about this because this is the last slide. I didn't get to it, so I'm just going to give it to you here. A very important consequence of the stationarity condition is as follows. If we know we have strong duality, so we're in a situation where the problem's convex and we have a strictly feasible point, say, over the inequality constraints, then if you give me a dual solution, u star, v star, then any primal solution, x star, must satisfy this stationarity condition, right? Because it's a necessary condition, so any primal solution must satisfy this stationarity condition, and I can just rewrite that as x minimizes the Lagrangian over all of Rn. Questions?
For any uv, not just dual optimal uv.
No, it has to be dual optimal uv because, right, I mean, we can think about it in several ways, but one of them is that if I have u, v, and x all optimal, then the stationarity condition has to hold. So if u, v are optimal, then if I want to have an optimal x, it has to minimize this at the dual optimal solutions. Okay, so this is just a consequence of stationarity. So it's a very simple statement, but it actually ends up being very powerful, and it's going to lead to, I think in the next example, and also in the next lecture in particular, a way to characterize primal solutions from dual solutions. Okay, so we can look at this, we can study this problem, or study its stationarity condition, which is this, and we can characterize primal solutions from dual solutions. And that's very helpful. If the dual is easier to solve than the primal, then we can solve the dual, and we can characterize primal solutions. So when can we actually get a primal solution? When can we actually get a primal solution from a dual solution? That happens if the solution to this problem is unique. Okay, so if there's only one solution to this equation, and I tell you that any x star must minimize this, then the minimizer of this equation must be x star. Right? So if it so happens that in addition to having strong duality, this also has only one minimum, this problem, a unique minimizer, then it actually gives us the primal solution. Okay, so are we all on the same page with that? Pretty basic point, but it's important. So here's an example from your book. And it's going to somewhat mirror what we study next time in the next lecture. But let's suppose we have a problem of this form where I have my primal objective function is just the sum of a bunch of coordinate functions. Okay, so f decomposes as a sum of fi of xi, where xi is just the ith coordinate of x, my primal variable. But I have this complicating constraint that ties all the variables together, A transpose x equals b. So if I didn't have this constraint, it'd be very easy to solve this problem. I could just minimize each of these in turn, right? But this complicates it by tying the primal variables together. And let's suppose additionally that each of these fi is a strictly convex function. Okay? Then if we derive the dual, how do we do that? Well, we just write down the Lagrangian. So we take this constraint, we multiply it by a dual variable, And there are no constraints on V because we don't have an inequality constraint, it's an equality constraint. Right, so I can pull out the BV out of the minimization, and I have a minimum over Fi of xi minus ai, the ith coordinate of this, this constant vector a, times v times x. If I want to minimize this over x, I can just do that for each component. And I'm going to write that minimum as the negative of f star sub I. And that f star is actually called the conjugate function of fi, and we're going to learn that shortly. So this equality right here is going to make a lot more sense to you once we talk about conjugates. But right now you can just think of this even as a definition. I'm calling this minimum this function, right? Because it's not a function of xi anymore, it's only a function of ai and v. So what's the dual problem? It's to maximize this, right? Or equivalently, I can say that I can minimize this. And this is a convex minimization problem, because the conjugate function is always convex, which again we'll talk about shortly. But the important thing is there's only one variable here. There's one variable, and that's v. So I went from a problem with n variables here, the primal problem, to a problem with one variable. So I can solve this easily with a bunch of different methods. Is there a question?
In the second to last line, shouldn't it be xi, ai, dxi?
ai?
Dxi?
No, because I'm minimizing over xi. Right? So there should be no xi's that appear in the function.
No, not the last one, the second to last. Yeah, to the right.
The last term.
This should be, thank you, yeah, it should be xi. Thanks. So this minimum is actually the minimum okay, so this is pointed out that should be an xi in the last term there. Thank you for the typo. Okay, so the dual problem has one scalar variable, right? And we can solve it in a bunch of different ways. We didn't talk much about univariate methods for minimization, but there are lots of different ways to do that. We can think about a bisection method, for example. So given that we've solved the dual, which is a much lower dimensional problem, it's just one dimensional, we know from the stationarity condition that any primal solution x star has to minimize the Lagrangian, right, which is this. So it has to minimize this, and the strict convexity of each fi implies that the minimum here is unique. So that means that once we've solved the dual, we can actually compute a primal solution by just for each xi solving a subgradient equation, right? Where I have to find xi such that ai times v star is in a subgradient of fi at xi. Okay, and if f is differentiable, then I can just write this as, for example, I want to solve this equation for xi, given that I found the dual solution v star, and that gives me the primal solution. So, yes, I could have. I mean, nothing would have changed except for I don't know that actually the minimum here is unique. So that means that if I minimize this, I don't know it's a primal solution. I know that any primal solution must minimize this, but not every minimizer of this is a primal solution. That's an important distinction. So if fi wasn't strictly convex, then each primal solution must actually minimize this, but not vice versa. But we're going to see that even in cases where it's not strictly convex, you can often characterize primal solutions in a way that's helpful.
Do you know the conjugates are convex?
Yes, we'll talk about that shortly. So there's some subtleties when dealing with duals, and I wanted to point them out. Often when we have a dual problem, like we did in this example, it'll be a maximization problem, and I can just say, oh, an equivalent form of the dual is just to minimize the negative of the criterion. Or I might drop constants from the dual criterion that don't depend on the dual variable. So often we'll transform it to an equivalent problem, and we'll still call that the dual. There'll be no distinction in terms of terminology, but we have to be careful that we don't ever fool ourselves by thinking that the criterion value at the optimum of the transform dual is equal to the criterion value of the primal at the optimum. That's only true about the original dual. Right? So if I get rid of constants from the dual criterion, or I reverse its sign or I do something to it, then at the optimum, the value of that criterion is not necessarily going to be equal to the value of the primal criterion anymore, because we transformed it a bunch. Even though the solutions didn't change, we are changing the value of the criterion. So just don't run into that issue, because it's a bit subtle. And another kind of subtlety when dealing with duals is that sometimes, or in a lot of cases, we can derive duals for unconstrained problems. Right, so that seems like a bit strange, because if I wrote down this problem to you, and I asked you what the Lagrange dual function was, strictly speaking, it's just a constant, and it's equal to f star everywhere. Right, because I have no constraints, so I have no dual variables, so the Lagrangian is just this function. When I minimize it over x, it gives me the primal optimal value. So how do we deal with unconstrained problems in duals? We often add dummy variables as an equality constraint. So I'll give you an example of this very shortly, but basically we might introduce another variable z, and then add the constraint that x is equal to z, and then I have a Lagrange multiplier for that constraint, and I can derive a dual. So different ways of transforming the primal problem to give us duals actually end up with different duals. Right, so I can take the primal problem, I can add constraints that don't matter, or I can transform it to an equivalent problem in one of many ways. And depending on which way I do that, the duals are going to be different, and they might be easier or harder. They're not necessarily all the same dual. Okay, so there's a lot of subtleties there. So you have to kind of make sure that you're thinking about all the different cases when you're looking at the dual. So here's an example of both the last 2 points. So we've studied this problem a few times, and it's going to be helpful to look at its dual in the next lecture in particular. So for the Lasso problem, right, I have the usual least squares loss, where y is my continuous response and a is my vector of my matrix of predictors. And I place a one norm penalty on x times a tuning parameter lambda to enforce sparsity in x. Okay, if I didn't have any transformations of this problem and I asked you what its dual was, its dual function would just be f star. It would be the optimal value of this. Right? That's not helpful at all. It's pretty useless. So what we do in this case is that we add a dummy variable. So we write this as this problem. So all I do is I add a variable z, and then I enforce a constraint that z is equal to ax, and I replace the ax and the squared norm with a z. Okay, so it's clearly an equivalent problem. Any solution of this is going to be a solution of this, and vice versa. But now we can actually derive a dual for this problem. Okay, so how do we do that? Let's just go through the motions. The Lagrangian looks like 1/2 y minus c squared plus lambda x1 plus the dual variable u times z minus transpose z minus ax. And there's no constraints on u because it's an equality constraint. So I want to minimize this over x. That gives me the Lagrange dual function. Okay, so I can split that up into the terms depending on x and the terms depending on z. I'm sorry. I want to minimize this over my primal variables, which in this case are x and z. So I can split this up into the two minimums. So first I'll look at z. So I have something like this. Y minus u transpose z. Right, so when I minimize this over z, this is just minimizing a quadratic, and it gives me 1/2 y squared. And this I take, right, minus, I think of minus b over 2a. A here is just a half, so it's the minimum is at y minus u. And when I plug in y minus u for z, I get minus 1/2 y minus u squared. And how do I do this minimization over x now? I think I'll write it below. This is over z. Now over x. The minimum over x of lambda of the L1 norm of x minus Z transpose X. It turns out, and again, this is why we're learning this stuff today, because they pop up so often. This is just the conjugate function, okay, or it's the negative conjugate function, but it's equal to either 0 or minus infinity. And it's, sorry, I had an A here, right? I don't have a Z. People probably recognize that but didn't want to say anything. The proper multiplier here on X is A transpose U transpose X. So it's 0 if A transpose U in infinity norm is less than or equal to lambda, and if it's greater than lambda, then it's minus infinity. Okay, so this comes from looking at the conjugate of the one norm function. We'll learn that shortly. Okay, so if I put these two things together, this basically puts a constraint on my dual variable u, and then this is the dual criterion. So therefore, the dual problem is just to maximize the subjective function subject to A transpose u and infinity norm being smaller than or equal to lambda. Okay, and I can write that equivalently as the minimum of just the squared error term, because y is a constant, and I can get rid of the sign and make it a minimum now, subject to A transpose u and infinity norm being smaller than or equal to lambda. So this problem, if I solve this for u star, and I solve the primal problem for x star, it would not necessarily be true that the value of y minus u star squared was equal to the value of the optimal Lasso criterion. In fact, it wouldn't, right? Because I got rid of y and I negated it. So if we're using the duality gap in some way, we have to use the original criterion. We can't use the transform criterion. Okay, now what happens if we look at the stationarity block of the KKT conditions over Z, right? So my primal, my Lagrangian was this, y minus c squared plus u transpose Z minus AX. And I know from the stationarity condition that that 0 must be a subgradient of this with respect to my primal variable. So I'm just going to look at that condition over just the Z block, taking a subgradient with respect to Z of this. There's a half here. And it's differential with respect to Z. So for example, that's just the gradient. So I'm telling myself that Z minus y plus u star must be equal to 0. That's the gradient with respect to Z. And if I plug in the value of the dual optimal point, then any primal solution has to satisfy this. If I rearrange this, I just tell myself that Z, which is equal to AX star at the solution, right, is equal to y minus u star. So that just came from the stationarity condition. And this is the relationship between the primal and dual solutions in this case. Okay, so any Lasso solution has to satisfy AX star equal to y minus u star, where u star is the solution of the dual problem for Lasso. So it's just the residual from solving the dual problem. Now if I had an X star that satisfied this, it may not be the Lasso solution if the Lasso solution wasn't unique. Right? Because, for example, if A doesn't have full column rank, then this defines a ton of solutions, an infinite number of solutions, and not necessarily every one of them is a Lasso solution, but every Lasso solution must satisfy this. Are there questions about that? Okay, so I'm going to leave this up to you to check at home, but you can check that had we taken our problem and we wrote it like this, like this, which is also equivalent. The only difference is that I've now substituted in Z for the X in the one norm rather than Z for AX in the squared error loss. This would lead to a different Lasso dual, different problem. That I think, I mean, in some ways is harder to solve and in some ways is easier to solve, but it's a different problem. So you can check that at home, go through the motions and look at the dual. Okay, so here's now what we're going to talk about today. We're going to define and talk about conjugate functions, which are kind of very essential when dealing with dual problems. Then we're going to talk about dual cones, which also are a very general concept that pop up a lot and are going to help us understanding dual problems. We're going to briefly talk about, if we get to them, dual polytopes and polar sets. So here's now the time where I try to tell you what's important and what's not. Knowing conjugate functions is very important. That's like bread and butter for deriving dual problems. So you have to be very comfortable with that concept. Dual cones are also important. I wouldn't say it's as important as conjugate functions, but they pop up a lot. Dual polytopes is not so important. I mean, it's an important topic, but not for the purposes of this class or, say, the midterm. But I wanted to cover it because when Jeff talked about polyhedra in one of the first lectures, he talked about being able to represent it in terms of either an intersection of half spaces or a convex hull of the vertices, and he called those primal and dual representations, and I was going to connect those two representations to duality through dual polytopes. Polar sets, I think, are helpful to know, also not super important for the sake of the midterm or this class, but they're a generalization of kind of everything in terms of geometric duality. So they encompass dual cones, dual polytopes. They also in some way encompass conjugate functions as well. So it's the most general form of geometric duality. And if we get to that, then we'll go over that briefly. Just to point out, there's a lot more concepts relating to duality, like dual graphs. That should say algebraic, not algebraic dual. The analytic dual, and so on and so forth. And you could go on a bender studying duals for a long time, but we're going to try to just restrict to these topics. If you're interested in some of these stuff, you can come talk to Jeff Fry, and we can try to explain to you how they relate to dual problems. Okay, so what's the conjugate function? Like duality in the KKT conditions, it's a very simple definition, and a bunch of very simple steps lead to some pretty powerful results. So if we have any function f, we're not talking about just convex functions, but functions in general, could be non-convex. We're going to define the conjugate function, which we denote by f star, to be the maximum over all points x of y transpose x minus f of x. That's the conjugate evaluated at y. So it looks at the maximum difference between this linear function of x and the function itself at x. Okay, so here's a picture taken from your book. If this is the function f of x here, and I ask for you what is the conjugate function at y, then I take this, in one dimension, I take a line through 0 of slope y, and I try to find the maximum difference between that line and the function at x. So it turns out that occurs in this example, say at this point. This is the biggest gap between the linear function and our function. Right, because this has to go through 0, I can think about shifting down to the function value and tracing it back until where it crosses the y-axis. And where it crosses the y-axis is negative the conjugate function evaluated at y, which is the same thing as saying it's just this gap. That's the conjugate function, difference between the linear function and our function. So this is always convex, f star, even if f is not convex itself. Why is that true? It's because it's a pointwise maximum of convex functions in y. So each one of these is actually just an affine function in y, right? So it's certainly convex. And if I take the maximum of a bunch of convex functions, I get a convex function. So I didn't need to use that f was convex there. So there's a bunch of properties that it satisfies. We're not going to, these are not very hard to prove. We're not going to go through them just for the sake of time. The first property is called Fenchel's inequality. I forgot to mention that if f is differentiable, the act of conjugation, or the transformation of conjugation, is just called the Legendre transform. So you might have seen that in another class. And sometimes people call this the Fenchel conjugate for non-differentiable functions to differentiate it from the differentiable version. But we're just going to call it conjugates. So Fenchel's inequality says that for any x and y, if I take f at x and I add its conjugate at y, then that's bigger than or equal to x transpose y. So why is that true? Well, number f, the conjugate of f at y is the maximum over all points x of y transpose x minus f of x. So in particular, if you just give me any x, right, then certainly this is going to be bigger than or equal to this because it's the maximum over any particular x, and that's where that inequality comes from. So very simple, but we're going to see this actually gives us forms of inequalities for different functions that are kind of like Cauchy-Schwarz inequalities. They're helpful. If I take the conjugate of the conjugate, which I'm denoting by f star star, then it's always less than or equal to f at every point. Okay, again, it's pretty easy to prove this. You can just go right from the definition and verify for yourself if that's true. If f is closed and convex, then if I take the conjugate twice, then I get back the function itself. Okay, so closed, we haven't talked about what it means for a function to be closed. There are many ways to define that. Any continuous function is closed. You can think about closed being something like, if I look at the epigraph of the function, then that's a closed set. Okay, or also all of its sublevel sets are closed. Both of those are equivalent to being closed. So pretty much every function that we're going to look at that's convex is going to be closed. If we take the indicator function of an open set, for example, like if I take the indicator function of the open ball, where it's strictly less than 1, say, that's not a closed function because its sublevel set, for example, any sublevel set is open. Okay, so but most functions we look at are going to be closed. So if f is closed and convex, then take the conjugate twice, I get back the function itself. And this is a very, very helpful conclusion that we're going to use when we talk about dual methods for solving problems like dual ascent and dual decomposition, is that if I look at subgradients of the conjugate at y, and I say what points x are subgradients of f star at y, then that's equivalent to looking for points y that are subgradients of f at x, which we know is actually equivalent to getting an equality in Fenchell's inequality. Okay, so I'm trying to think whether I should prove this now based on the amount of time we have. I'm just going to prove it very quickly and make sure that you understand the proof by looking back over it if I've gone too quickly. So remember we talked about the subgradients of maxima when we talked about subgradient calculus, and we talked about under certain conditions, actually those conditions are exactly satisfied if f is closed and convex, that we could write this as the convex hull of the union of all points x that achieve that maximum. So remember, if f star is defined like this, for x to achieve the maximum, it means that y transpose x minus f of x is equal to f star of y. And then I take the subgradient here with respect to y of those functions, and that's what I take the union of. So what's the subgradient that's with respect to y? It's just x. Okay, so given this, now you can see why that's true. If I have any x that's in the subgradient of f star of y, then I can write it like this. So that gives me this inequality. And because it's a minimization problem, I can look at the subgradient equations for this. I can write this as a minimization problem, right? Minimize f of x minus y transpose x. And that'll imply that y is a subgradient of f of x. So this equality basically tells us how to compute subgradients of the conjugate function. Okay, so this is an important one to remember. So just some examples. Yeah, question?
The part about the convex hull, it's not exactly
Yeah, so you can verify that. I think Martin's asking the question, if I have a point in this convex hull, I don't know it's actually in one of those unions, but you can show that if the point's in the convex hull, then it'll also achieve the maximum. Just plug it in and you'll see that's true.
So a useful special case of that is if the function is differentiable, then the subgradient of the dual is the inverse of the subgradient of the original function.
So I think, so Jeff is talking about the differentiable case, and we're going to focus on that next time as well. I guess we can write that. I can just write the differentiable case here if you'd like. So we said that x is in the subgradient of f star at y if and only if we had something like x transpose y equals f of x plus f of y star. Or another way of writing that is x maximizes z transpose x minus f of, z transpose y transpose z minus f of z over all z, right? It maximizes this over z, just from the definition of the conjugate function. So if f is differentiable, then there's only one subgradient, and that's the gradient. So that means that there's a unique maximum in this problem. So I can actually write it like this, that the gradient of the conjugate function is equal to the point that maximizes this difference. Okay, so this is what the differentiable case reverses. This is what it reduces to. Okay, so just to go through some examples of conjugate functions, I'm going to skip the first one just for the sake of time, but if you have a quadratic, and its conjugate is a quadratic with the matrix, the quadratic form matrix inverted, essentially. And Fenchel's inequality gives us this inequality, which is somewhat non-trivial, right? That was a trivial thing to prove from the definition of conjugate functions, but this is, I think, if you look at this, this is not immediately obvious why this is true for all x and y. Indicator functions, we're going to do this one because we end up using this a bunch. If f is the indicator function of a set C, so it's either 0 or infinity. If x is in C, and if x is not in C, it's infinity. Then its conjugate function, right, it's just kind of a silly thing to write down. It's equal to the max over all x, say, of y transpose x minus f of x, right? But this is equal to infinity, so this is equal to minus infinity if x is not in C. So it's like saying that I want to take the maximum and just restrict it to looking at x and C. And that's called the support function of the convex set C. So another important thing to know about, and it's just a special case of conjugate functions. And we're going to note it by I star of C because we use the notation I of C for the indicator function. Okay, we'll revisit that later. Norms. Here's another important one. So I claim that if you have f of x equals some norm x, this is very helpful for deriving dual problems when we have norms in the criterion. Then if I take the conjugate of that, then it's equal to 0 if the dual norm of y, the Freudian slip, I was writing it as infinity because we talk about the one norm a lot. If the dual norm at y is smaller than or equal to 1, and it's infinite if it's not. So it's the indicator function of the dual norm unit ball. Okay, and again, I'm not going to prove this. The proof is on the slide. It's pretty detailed. And make sure you follow that. But an important thing to remember. Okay, if we have a norm, we can always look at its conjugate just being the indicator of its the dual unit ball. So it ties in the dual norm, which we also learned a couple times throughout the course. So why are conjugates useful for dual problems? It's because of this. It's because of the fact that the negative conjugate at a point u is equal to minus the minimum of f of x minus u transpose x over all x. Right? Usually it's just the maximum of the negative of this, but I can pull the negative outside and make it a minimum. So again, very simple thing. This is not like shocking, but you can see that in the terms of the Lagrangian, this is starting to look like what we do with dual problems. I have, say, my primal criterion, and if I subtract off the dual variable times one of my primal variables, then forming the dual criterion we do by minimizing this over x. And this is exactly the definition of the negative conjugate function at u. Is there a question? Sorry. So let's see. Yeah. The slide is correct. So it's usually defined as the maximum of the negative of this, right? So I can pull out the negative, and then I can put on the other side, and then I get rid of this negative here. So thank you for catching that. Okay, so let's consider an example where we have our primal criterion being the sum of two functions. So let's suppose that we want to minimize f of x plus g of x over all x. We want to know what's the dual of that problem. So again, we're going to do this trick where we add a variable and then we add a constraint. So we're going to rewrite this as f of x plus g of z subject to x equals z. And now I have two optimization variables. And I form the Lagrangian, and it's f of x plus g of z plus u transpose z minus x. Right? And I can rewrite that as f of x minus u transpose x plus g of z plus u transpose z. And if I minimize this over x and z, then what comes out is just exactly the conjugate function, the negative conjugate function of f at u minus the conjugate function of g at minus u. Right? Because usually it's defined as g of z minus some variable transpose z. So I put a minus minus, that's why I get a minus u there. Question? A hack? Yeah. Yeah. So that's, I mean, that's a good question. I was trying to kind of emphasize earlier that for unconstrained problems, we have no choice but to introduce dummy variables. We don't know what else to do. We can't drive a dual otherwise. In this case, it's obvious what to do, right? If I write you like this, there's one choice. I make one of them a z, and I have an x equals z. There's no ambiguity there. For this Lasso problem we studied, there is a choice here. I can stick the z in two places, and I get different duals. So my suggestion is to derive both of them, and then to look at which one looks more tractable. So explore all the possibilities, which usually there's a finite number, and then look at the different duals. So this dual didn't depend on A inverse. But if you derive the dual the other way, that I told you to do at home, you're going to see the dual actually depends on A inverse. So if you want to solve the dual, you'd have to invert A. And usually that's costly, so that's why I'd prefer this dual. So you can kind of do more work than you need to, and then in the paper you write, you can just put the dual that looks better. No, I'm just kidding. You should probably be explicit, but make sure you try all the different cases. Okay, so what we ended up with from this calculation that we did is that the dual problem looks like this. Maximize, I'll just write it here. The dual problem is maximize over all u the minus conjugate of f at u minus the conjugate of g at u. This is the dual objective. Oh, that's the dual problem, sorry. So there's a symmetry here, a nice symmetry right between the primal problem and the dual problem in terms of their conjugates. So we can immediately just apply this last calculation to a bunch of problems, and we're going to get the duals, given that we know what their conjugate functions were. We just talked about that a few slides ago. So what if I have a problem that looks like this, right? The minimum of f of x plus the indicator function that x is in some set C. So that's like doing constrained minimization over C. What's the dual problem? Well, let's just read off our rule. It was maximize the negative conjugate of f at u minus the conjugate of this function at minus u, and this was the support function. And again, we'll revisit this later, but we can actually, you can see already that if this indicator function was the indicator of a norm ball, then this is going to be equal to the dual norm as a penalty. Okay, you can think about that in multiple ways, but you can think about it like taking the conjugate twice. So go back and look over how we define support functions and dual norms, and you'll see that equivalence. Okay, in a lot of other cases, the support function, we know what that is also. So how, question? Yeah, definitely. This should be, that doesn't even make sense because there's an x in that equation. This should be f star of u. So I'll make sure to correct that. So how about norms? This is a case we deal with all the time. And if you go back over this, you'll see that the calculation we did for the Lasso, which is a special case of this. If we have this problem, for some norm, then again, we're going to read off this rule. Its dual problem looks like this. And I'm going to add here, or I'm going to subtract here, rather, the indicator function that the dual norm of u is smaller than or equal to 1, evaluated at minus u. Right, because the conjugate of the norm is the indicator of the dual norm unit ball. And I can write this as the same problem, as maximize the negative conjugate of f subject to the dual norm being smaller than or equal to 1. Right, because, we know that if I take the norm of minus u, it's the norm of u, so that's why the constraint looks like that. Okay, so immediately useful for a lot of penalized problems now where we add a norm. Here's a question that we kind of touched upon a bit last time, or maybe it was 2 lectures ago. Double dual. What happens if we take the dual twice till we get back to primal? That was true with linear programs, but is that true in general? So conjugates provide a way of answering that. So if we have this problem here, minimize f of x subject to, say, linear inequality and equality constraints for now, then through a short calculation, we can see that its dual is again defined in terms of the conjugate functions. Right, the conjugate function of f evaluated at some linear transformations of our dual variables minus some linear terms subject to u being non-negative, right? Because u is the multiplier, let's say, for this constraint, and v is the multiplier for that constraint, so we need to make it non-negative since it's an inequality constraint. So we have this property that f star star equals f if f is closed and convex. So again, I'll leave it up for you to check that when you take the dual of this, and if you use the fact that f star star equals f, you get back exactly the primal problem. So now we know the answer to this question. If f is closed and convex, if I have linear inequality and equality constraints, then the dual of the dual is the primal. So we haven't created new problems out of thin air. Right? There's a closed loop there. That's good. Yep.
Is the conjugate a good way to calculate the dual only if the constraints are linear?
So the question was, is it useful to calculate the dual when the constraints aren't linear? And yeah, it is useful. For example, right, in this case, we didn't have a constraint, but we had a nonlinear part, and we took its conjugate. And even in this case, the constraint could have been a norm constraint. I didn't make this explicit, but I can write on the slide if you'd like, on the paper if you'd like. If C is something like the norm ball, the unit ball for some norm, then the support function of C is the max over all y in C of y transpose x. And if you remember how we define dual norms, that's exactly the dual norm evaluated at, should have been a u in here, the dual norm of u. Okay, remembering how we define dual norms. So that means that if I take this problem subject to x in the norm unit ball, and I derive its dual, then I get this problem. Should be a minus here.
In the line beginning IC star, it should be x and c, not 1 and c.
Yeah, thanks. Okay, so here's an example where the constraint wasn't linear, right? It had a constraint like a norm constraint. And I used the conjugate arguments to get the dual explicitly, which ended up just adding the dual norm to the objective, or subtracting it in this case from the objective. Using the, so sorry, repeat that one more time.
Are you suggesting that this dual is useful when you have or when you can make up a constraint that you know what the dual definition is?
Okay, so yeah, the question is it basically the case that if you know what the conjugate of some function is, then that's when you add a constraint because you can get the conjugate and therefore you can get the dual problem. In these examples, yes. So I am using known conjugates. And it is true for a pretty wide class of functions. We know that their conjugate is in closed form. It's actually even useful to look at conjugates and dual problems when you can't write them in closed form. And we'll talk about that next time. There's a horde of methods that I guess I'll call dual gradient methods, where even if we don't know whether the conjugate is in closed form or the dual is in closed form, we can still minimize them. And it's using this, just to give you a preview, it's using this right here. It's using the fact that we can compute subgradients of the conjugate by solving something not involving the conjugate. A lot of good questions. So I went and looked this up because I was curious and I didn't know the answer, and I wanted to make sure I wasn't going to tell you something wrong. And it turns out I actually didn't know this fact, so you learn something new all the time. If you have this general problem where I minimize, f subject to some constraints not necessarily linear, and I say that f and hi are convex and closed, it's a very general condition, and the Lj are affine, so just look at this general convex problem, then it turns out that the dual of the dual is the primal. That's true in general. And there's this very neat way of looking at this entire minimization problem as something called a bifunction. So essentially it's a function of the primal variables and something else that we haven't talked about in class, but that are perturbation variables that we would put on the right-hand side here. And then the act of conjugating that function is exactly the dual. So the conjugate is actually, in some sense, encompasses program duality, because I can think about driving the dual problem of this as taking the conjugate of some kind of master function, very, very big, high-level function. And if you take the conjugate of that function twice, it gives you itself back, provided that function is closed and convex. In other words, if I take the dual of this problem twice, I get back the primal, provided that these functions are closed and convex. So there's an exposition of this in Rockefeller. I have to say it's not the easiest thing to read. So again, if you're feeling giddy and brave, you can go ahead and read chapters 29 and 30, or you can just trust me that I'm quoting the results faithfully from those chapters. So something Yeah, something new for me at least. Cones. Okay, so we're going to start with, again, something pretty simple, and it's going to give us something quite interesting. A set's cone if we can just take positive multiples of points and that they still lie in that set. Okay, so if x is in k, that implies that theta of x is in k for all non-negative theta. Was there a question? Okay, so that's a good question. I don't want to answer that because it's going to take me too long to go into basically the content of these chapters in this slide. But you will get back a problem whose solutions are the primal solutions. I'll just put it that way. I mean, yeah, again, I don't want to answer that because I think there are conditions under which you do. But I think it would... Well, I can always add. I mean, if I have the primal, I go to the dual, I derive the dual, go to the dual, and then I change the dual and I derive the dual of that. It might be different, right? So sometimes it might be not tractable or not easy to derive the dual of the dual unless I transform it. And once I transform it, I take the dual, I might get something different than the primal. But if you're able to, if you can make that exact correspondence between primal and duals, then they come back out the same. So cones. Convex cones are stuff that are both convex and cones. So they look like this, basically. In two dimensions, it's everything in this region. So the property is that if I have 2 points in K, that implies that I can take positive multiples of those points and add them together, and they have to be in the set for all theta 1 and theta 2 non-negative. So what's the example of something that's a cone but not convex? Can somebody think of an example of that? Yeah, right. So the simplest example is just this. Right, so I'm not filling anything in. I just have this line, say, and this ray and that ray. So it's a cone, but it's not convex. It's a cone because if I take any point here and I take a positive, this is 0, I'm putting these at 0. If I take any multiple of that point, it's going to be in the set. Right? The multiples of this point that are positive lie along this ray. If I take any point here, multiples of that point are going to be on that ray. But it's not true that it's a convex cone, because if I take this point plus this point and I take some combination of them, there's something in here, and that's not in the set. So some examples of cones. Any linear subspace is a cone. Right? In a linear subspace, I can take any linear combination of points and it's in the space. So certainly non-negative combinations will be in the space. We have a class of things called norm cones. So that's something that looks like, if the norm's on Rn, it's a cone in Rn plus 1. And it's the set of all x and t for which the norm of x is less than or equal to t. So this is just the epigraph of the norm function. Right? And if I have a 2 norm, then there's a bunch of different names for this. I've heard it called the Lorentz cone, the second order cone, the ice cream cone. It's something that people study a lot because we're going to see, as it turns out, that it's self-dual. So the dual cone of this cone is itself. But here's what it looks like in 3 dimensions. It just looks like this, right? It goes up like this, as we, I guess, intuitively expect cones to do. What does this look in 2 dimensions? So in 2 dimensions, the Euclidean norm is just the absolute value, right? So it would look like this. And now, of course, I've hit something. Okay, there we go. So the normal cone, we talked about this earlier in the class. Remember, the subgradients of indicator functions are the normal cones of convex sets. Or it doesn't have to be a convex set. It's a normal cone of the set at that point. So how do we define it? If you give me a set C and a point x, then the normal cone at that point x, with respect to the set C, is a set of all vectors g for which x maximizes the inner product with g among all points y that are in the set. So g transpose x is bigger than or equal to g transpose y for all y and c. That's the normal cone of the set at x. And here's some examples of what it looks like. On the boundary, the normal cone is just a ray for these curved boundary points. And then if I had a point like this in the boundary, then the normal cone actually has a non-empty interior. Okay, and the normal cone inside the set is just 0, the set containing 0, which is a trivial cone. So this is always a convex cone regardless of C. So C could be non-convex, it's still a convex cone. Positive semi-definite cone, this is an abstraction on the set of matrices that are symmetric and positive semi-definite. So look at all the matrices X that are an n by n. They're symmetric and they have the smallest eigenvalue is non-negative. Then this is a convex cone. How can we check that? It's very simple. Just take A and B that are symmetric and semi-definite. Take any two theta 1, theta 2 non-negative, and form this combination, theta 1A plus theta 2B, and just check directly that X transpose that matrix times X is always bigger than or equal to 0. Right, that's definitely true because I can split it up like this, and all of these terms are non-negative. That's also a cone. So the reason we're talking about it in this lecture rather than another lecture is that there's something very natural about cones, relating cones to duality, and that's through the use of what's called the dual cone. So I have a cone K. I define the dual cone to be the set of all y for which y transpose x is bigger than or equal to 0 for all x in K. So let me just write that down and we can draw a picture. Okay, so it's the set of all y for which it has a positive inner product with x for all x in the cone. That's called the dual cone. And you can check directly from the definition that this is always a convex cone, even if K was non-convex. It's still a convex cone. So again, the ties to like dual programs and to conjugate functions, which are always convex, even if the original primal problem or even if the original function wasn't convex, are evident here. This is always convex, even if the original cone was non-convex. So what does this look like if we have a cone? Then this says that y is in K star if and only if this half space, set of all x for which y transpose x is bigger than or equal to 0, contains K. Okay, so if I take some point y and I look at the half space for which all points have a positive inner product with y, that's some half space like this, and since that contains my cone, then the dual cone contains this point right here, y. Okay, but if I look at, for example, this point, z, and I look at the half space for which everything has inner product positive with z, and that's something like this half space, right? And that doesn't contain the cone entirely. So this point's not in the dual cone. So you can imagine sweeping through space and define the dual cone in terms of which of these half spaces contains our original cone.
The single cone still with a rotating reactive.
No, it's not always true. It's not only a rotation. So like the dual cone could be strictly larger than the original cone. In fact, in this case it will, right? So if I have this example, the dual cone will extend everything from here to about here, right? Because I'm just taking the orthogonal lines to each of these lines, and then if I take any of these points between these two lines, that'll give me the dual cone. So this whole thing is the dual cone.
In general, the relationship between a primal and a dual cone can be pretty complex and non-obvious, right? So in 3 or more dimensions, like in 2 dimensions, cones are pretty simple. They have 2 bordering rays, right? But in a lot of dimensions, you have facets and extreme rays, right? And the number of those can be very, very different between the primal and dual cone.
Okay, we're almost in time for a break. I'm going to skip the examples. You can go through and check that these dual cones make sense. I'm just going to say what the results were. The dual of the norm cone is the norm cone of its dual norm. So another relationship there, and it's also a tongue twister. That also tells us that the dual cone, or the dual of the ice cream cone is the ice cream cone, right? Because the 2 norm is self-dual. Because 1/2 plus 1/2 is 1. The positive semi-definite cone is also self-dual. Okay, if we take the dual of that cone, we get exactly a set of positive semi-definite matrices back. So very quickly, dual cones and dual problems, how does it tie in? It just comes from this idea that we talked about with conjugates and support functions. So just from our work on conjugate functions previously, if we have a cone-constrained problem, so I'm minimizing f subject to x lying in this cone k, then its dual problem from what we derived is equal to the negative conjugate of f at u minus the support function of this cone at minus u. Okay, and let's just look at this for 1 second. This is equal to the maximum over all, say, x that are in k of minus u transpose x. K, and remember, k star was the set of all y such that y transpose x is bigger than or equal to 0 for any x in k. So what happens if minus u was in k star? If minus u was in k star, that means that when I take let's first think what happens if minus u was not in k star. Okay, that means that there's some u is not in k star. Then that means that there exists some x in k such that u transpose x is strictly positive, or strictly negative. Goodness. Okay, but because it's a cone, that means that I can make this as large negative as I want. Right? I can just multiply x by tx, let t go to infinity, and this can become as big negative as I want. Which means that this maximum can become as large as I want. Right? It's infinity, essentially. And what happens if u is in k star? That means that u transpose x is bigger than or equal to 0 for every x in k. Right? So the biggest that minus u transpose x can get is 0. I just take 0. So we've just proved that the support function for this cone is exactly the indicator function of the dual cone. Okay, so that means that this dual problem that I wrote up here, I can rewrite this as maximize minus the conjugate function at u subject to u being in the dual cone. Okay, so another nice symmetry here. We have a cone-constrained primal problem. We have a dual-constrained, a cone-constrained dual problem, and the cones are just the duals of each other. Let's take like a very quick couple-minute break, and then I'm going to come back and try to tie this together. Okay, so we're going to try to finish our super fast tour through duals. It looks like I'm not going to get to polytopes or polars, which is okay because I told you they weren't important. So if you want to look through that, please do, and I think it's a useful reference for maybe your different types of convex analysis. So go ahead and look through that, but you're not going to be tested on that in any form on the midterm or on homeworks. Okay, so we just talked about dual cones and dual problems. Cones do this nice thing for us because they define something called generalized inequalities. Okay, so you might say, well, how useful is this relationship because cones seem kind of special? I'm just going to try to argue for you for the rest of the class that cones are pretty general, and a lot of things that we study already can be written as cone constraints. So knowing this trick is actually quite helpful. So cones induce something called a generalized inequality. And we write that as less than or equal to sub k, where k is the cone. And we just say that x is less than or equal to y with respect to this cone k if the difference between y and x is in the cone. Okay, so this is a definition for this inequality. And some examples of it are a component-wise inequality. So if I wanted to think about an inequality that says that x is less than y in every component, then that's actually just this generalized inequality if I take k to be the non-negative orthant. So that if I define k to be this cone, which is the set of all x such that xi is bigger than or equal to 0 for any x, then x less than or equal to y with respect to this cone is saying that xi is less than or equal to yi for any I. Okay, so we've been writing this just as this. We've dropped the k because that's very natural for vectors. But that's an example of a generalized inequality on cones. This matrix inequality is also another example of this. So if we take k to be the set of positive semi-definite matrices, then x is less than or equal to y with respect to this cone. It means that y minus x is positive semi-definite. I'm actually going to get rid of that because it's going to be kind of circular. But this just means that this matrix has its smallest eigenvalue non-negative. Okay, so we've actually been writing this as this for matrices because, again, we thought it was very natural, but it's precisely defined by generalized inequality on this cone. And there are many more examples. So anytime we have constraints on vectors that are component-wise or constraints on matrices that are these positive semi-definite constraints, they're actually just cone constraints. You can think of them like generalized inequalities and hence cone constraints. So that encompasses a lot of the stuff we've done. For example, everything with linear programs so far. These are very useful things to know about, these conic solvers. And there are two that I can think of that are that stand out particularly. There's CVX and there's TFOX. So CVX is a software package that's written by one of the authors of your book, Steve Boyd, and someone else. And TFOX is written by that someone else and some other people as well. So they're kind of competing, but they share a common author, so it's a bit interesting in that regard. But essentially, both of these two software packages, they try to take any problem you give it that's convex and turn it into a cone constraint problem. And they can do that with remarkable success for almost any convex problem you give them. They figure out a set of cones, and that's another talk in and of itself, another lecture in and of itself. But they figure out how to pose convex constraints in terms of cone constraints, because it's very, very general. Then when they have that conic form, they go off and they do their thing. And that's where they differ. So CVX is very general. It's actually more successful at turning in a lot of problems into cone problems, so it can solve a lot more general problems. TFOX is less general, but it's a lot faster, okay, because it looks at a more restricted class of problems, and it ties in nicely with the stuff we've been talking about, because it takes the dual of those problems and solves the dual. And apparently, according to the papers that's been written, it gets close to state-of-the-art, which is remarkable that such a general tool could get close to state-of-the-art for such a broad class of problems. Bless you. Okay, so that's about as much time as we have. I have the reference here for TFOX and CVX. TFOX, like I said, ties in particularly well into what we've talked about. So please do look that up if you're interested. And like I said, polytopes and dual polytope and polar sets, look them over if you're interested, but don't worry about them for the upcoming classes. Okay, see you guys on Thursday.